Today we are going to explore something exciting that is nothing but quantum computing and quantum parallelism. Quantum computing and quantum parallelism. We'll start how quantum computing began, understand what makes it so special, and finally see how it can do many things at once faster than a normal computer. So, in 1940s and 1950s, computers like ENIAC and UNIVAC were built. ENIAC is nothing but electronic numerical integrated integrated and computer. Okay, whereas UNIVAC stands for universal automatic computer. So it was built in 1940s and 1950s. So they used bits. Okay, what they have used, they have used bits. That means each tiny unit of information could only be either 0 or 1. Even today, our phones and laptops use the same idea. So, but scientists discuss something amazing, that the world of tiny particles like electrons, photons, does not follow simple rules. They exist in many steps at once. So the idea came from quantum mechanics. In 1981, a physicist named Richard Feynman asked, okay, I already explained this. If nature itself a quantum, should not why should not our computers are also work like that? So the question gave birth of quantum computing. From there on, we have been seeing about quantum computing. So the main part of quantum computer is called a qubit, short for quantum bit. A normal bit can be either 0 or 1, but a qubit can be 0, 1, and at the same time it can be 0, 1. So we call it as superposition. So we write it as ket psi is equal to alpha ket 0 plus beta ket 1. So here alpha and beta show how much the qubit behaves like 0 and 1. Okay, when we measure, it becomes either 0 or 1. So it is like tossing a coin while it's spinning. It's both heads and tails together. But when it lands, you see only one result. Either it can be heads or either it can be tails. So now comes something magical, that is nothing but entanglement. So when two qubits are entangled, they become linked. If you change one, the other changes too. Instantly, even they are far apart. Okay, so the formula is for uh, the cube entanglement is nothing but ket psi is equal to 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 1. So here, if you measure first qubit as 0, second qubit will always be 0. If you measure first qubit as 1, second will be always 1. That is what entanglement says. It's like having two magic coins. If you flip one and get heads, the other one immediately shows heads. So no matter how far they are, this is strange connection allows like things like quantum teleportation, super secure communication. Okay, this enables them. Okay, now quantum computing started just a theory, but in 1980s, Feynman and Deutsch proposed the idea. In 1990s, scientists developed special algorithms like Shor's and Grover's algorithm, which showed that quantum computers could solve some problems much faster than the classical computers. In 2000s, labs began making small quantum systems that are nothing but ions and photons. So in 2010s, companies like IBM and Google built real prototypes, and in 2019, Google's computer called Sycamore performed a task in minutes that would take a normal supercomputer thousands of years. Thousands of years it may take for supercomputer to solve that problem. That was called quantum supremacy. Now we have systems with thousands of qubits and we are working towards large stable quantum computers. So that is the future. So why quantum computers are powerful? So quantum computers are powerful because they think differently. So they don't process one path at time, they explore many paths at once, that we call it as superposition. They can solve complex problems much faster than normal computers. So and the best part is nothing but their security is based on laws of nature, based on physics, not max. So you can when so you can say a quantum computer does not think faster, but it thinks in all directions at once. So now moving on to the concept of quantum parallelism, that is nothing but many states at once. Now let's see what really makes quantum computers magical. That is nothing but quantum parallelism. In classical computer, we handle one input at a time, but a quantum computer, because of superposition, can handle all possible inputs at the same time. So that means it can test many options at once, something classical computers cannot do. That is called quantum parallelism. So now how this quantum parallelism works? Let's take a simple example. Suppose we have a function f of x that works on two inputs, 0 and 1. A normal computer first checks f of 0 and f of 1, that is nothing but two steps. But a quantum computer makes both steps exist together, so it can check it in one single step by using this formula. This is nothing but oracle box. I will explain this in the next video. Okay, that is why it is called parallelism. So it is doing many calculation at once inside the same operation. So that is the reason quantum parallelism is so powerful. So I have given one quick example of real life. So think of this like searching for treasure behind two doors. A classical person opens one door, checks, and then opens the other. But a quantum person can open both doors at the same time. That is nothing but superposition. That's how quantum computers work. They explore all possibilities together and find the answer faster. Okay. So now interference. So however, even though quantum computers can check everything at once, we can only see one answer. When we measure, we only see one answer, not 0, 1. Okay, that you need to remember. So how do we make sure it gives the right answer? So this is where interference comes in. So quantum systems mix their results. The wrong answer cancel out, called destructive interference. So these are nothing but wrong answers, and correct answers get get one stronger, that is nothing but constructive interference. This makes the correct result more likely to appear in the output. Okay, these are the two types of interference. So quantum parallelism is used in many famous algorithms. That is nothing one is nothing but this algorithm which helps test if a function behaves in uh, the same or differently. Grover's algorithm spends up searching of an item in a large list, whereas Shor's algorithm breaks big number encryption. And Siemens algorithm helps find hidden patterns. All of these take advantage of the fact, okay, the quantum computers can explore many possibilities at once. So what is the future? Right now, our quantum computers are still in the early stages. So we call it as NISQ era. Okay, noisy and small scalable machines. But the future is bright. Quantum parallelism will power quantum AI for faster and smarter learning. Quantum parallelism will power drug discovery to simulate molecules. Quantum parallelism will power secure communication. Quantum parallelism will power optimization for logistics and investments. So the ultimate dream is a quantum internet where quantum computers all over the world connect using entanglement and sharing the information instantly worldwide. So thank you. If you are having any doubts, let me know in the comment sections.